Okay. Let's do some examples. So just as a reminder, and I'm starting to see some of this, the next assignment is really going to start looking at work energy. So assignment 9. And then the last assignment is assignment 10. You are free to do more work if you wish, and you should, because we are going to cover vibrations in 8 days. So let's start with this one. I have a stick. It's length L, mass M, and I'm asked to find the value of theta at which the end A starts to slip. So force F and N are the friction and normal forces, theta, theta dot, theta double dot, F and N for acceleration G. Use work energy to find theta dot squared as a function of theta, and then find theta double dot, and finally plot force over normal as an absolute value. Okay. So you're looking at a problem where it starts at a position and ends at a position. And all you care about with a rigid body in terms of change in potential is the change in the center of mass. So it goes from the top and it swings down. You don't care what the difference is in the bottom or the top. You care about what the difference is in the center of mass. So if I look at this particular case, I have weight, I have normal force, and friction. The only other thing that I kind of need to know here is theta. So theta just gives me the angle at which this thing is at any arbitrary instant. The normal force just tells me what's sort of opposing motion, and that will be, of course, important for my friction. Mu sub s is given as, say, 0.7. And weight. So what I'm looking at here is a problem where I have sum of forces in the x direction, sum of forces in the y direction, mass times acceleration gx, mass times acceleration gy. I have the terms. So if I look at sum of forces in x, it's going to be F equals m AGX, and for y, I have sum of forces in y. And so the total, all of the terms there, I mean, this in terms of solving or looking at these terms, this is straightforward. It is hard to draw this free body diagram because you often wish there's more to it than what's actually there. So you have sum of forces in x, sum of forces in y. We start solving for it. This looks relatively straightforward. I'm going to go back to this drawing. I got mg, normal force. And I'm just going to add a little bit more. So I have the length of both, so L over 2 to G. And from that, I can start to put together some terms. VGX equals 1/2 L theta dot cos of theta. VGY equals 1/2 L theta dot sine of theta. All right, so all I'm doing is I'm taking the rigid body rotation, assuming it's sort of planted down there, and it's rotating about there. All right, all VGs. I also know x sub g equals 1/2 L sine theta. Y sub g equals 1/2 L cos theta. And as a reminder, that's theta. So we have all of the information that you need in order to sort of extract out things. So good, good, good. We got forces, we got normals, everything's there. Oh, that's going to appear a little bit earlier. Ignore that for now. So if I take the derivative of x and I take the derivative of vgx and the derivative, with that derivative I have agx, I can do the same with y, vgy, and agy. So the terms that I'm missing from my expression sort of end up being force of x equals magx, force x, or force friction, sorry. Force 1/2 mass times L times the mass up there. So 1, 2, 1. Okay. So I have then an expression for the friction force that could be useful to look at what's happening here. For the normal force, I can say N equals mg times 1 minus L over 2g theta double dot sine theta plus theta dot squared cos of theta. Okay, all right, clearly it's kind of a ridiculously difficult problem with variables, but it's a problem that's kind of useful to go over just to understand some of the, how to define things. And this second expression right here is your equation 2. All right, I have all the terms I need. And typically, and this is something I kind of recommend you do anyways. I think I've sort of said it enough at this point. You should draw the two positions out. So this is position 1, this is position 2. You know that that's theta. And okay, you can say at this point T1 is equal to 0, T2, V1 equals mg L over 2. And again, remember one of the reasons why you draw out these diagrams is so that you don't make a mistake later on and say, hey, I want it at the top. You want to know that you have an L over 2 there. So you have the terms there, and it's L over 2, L over 2. So you know where the height is. You do the same thing with your other term, T2, which you know is going as 1/2 I theta dot squared, IA theta dot, sorry, A is down here. So the point of contact. And again, at this point in the course, you know that that IA is 1/3 ml squared. You know that because that's a long slender rod pinned at an end, or at an end. Height, V2 equals mg L over 2 cos theta. I'm going to add this in anyways. Because I'm not going to recalculate it. But if you put all the terms in, you know theta, or you know everything's a function of theta, so you can write everything out, and you end up with theta dot squared equals to 3g over L, 1 minus cos of theta, which is kind of useful. That sort of gives you part of it. And if you are ever bored and you want to look at the Lagrangians, you can do those. There's a set of summary videos on them, but it's a similar approach with this. But here, all I'm doing is I'm taking the derivative with respect to time of both of these. Now, I'm going to end up out of this with an expression that goes as theta dot, or theta dot, theta double dot. And so I get 2 theta dot, theta double dot, which equals 3g over L sine of theta, theta dot. Tunk, tunk. Which is kind of an interesting result because now I can get rid of the theta dots on both sides. And out of that, I immediately get my alpha or theta double dot. So theta double dot is 3/2 g over L sine of theta. Your friction force is 1/2 ml theta double dot cos of theta minus theta dot squared sine of theta. Your normal force, again just substituting in terms, mg 1 minus L over 2g theta double dot sine of theta plus theta dot squared cos theta. So F, if you sort of crunch everything down, is this. N is this, which is kind of nice. So now I have a value for the friction force. I have a value for the normal force. Everything in terms of theta. So similar sort of orders, terms are sort of appearing. mg, everything else works. But what I know also is that friction is mu sub s sub n for all of this to be true, which means mu sub s equals F over n. And I'm going to look only at the magnitude, because if I look only at the magnitude, then I have something easier to deal with. Well, it also allows me to have negative forces and all of that. It doesn't matter what direction things are happening. So that leads to this relationship, which ends up being 3 sine theta, 3 cos theta, minus 2 all over 1 minus 3 cos theta squared. And that will give me mu sub s. So for this to be true, I can then plot all of this out. I can look at a number of different thetas and a number, well, thetas. So if I do that, I go back to this plot I put far too early over here. And I'm not going to try and sort of plot it out. But basically, I can minimize my mu sub s for different values of f over n and the corresponding, or for different values of f over n, the minimum value ends up being 0.84. And if I go beyond that, I'm going to end up sort of asymptotically approaching a crazy case where I can't deal with it. All right. Now, in this particular case, I snuck it by you very quickly and cleverly. I put a value of mu sub s equals 0.7. And the reason I put that value in was just to see what would happen in terms of what that minimum value could be. So in that case, so for mu sub s equals 0.7, you can solve for the roots. And in this case, I use Wolfram alpha. That's one word. Theta slip is equal to 0.9237 rads, which equals 52.92 degrees. That's kind of a wild problem. Lots of things happening. Questions? This is not something that we would ask you to do on an exam, just 1 second, but it is something that I think you should be able to handle. So it's something that you should be able to look at. You have to be able to draw the free body diagram. You have to be able to look at certain features. This step to this step, you kind of have to remember definition. But that's not a bad step. There's a lot of work involved in terms of deriving this, but it's not a lot of very hard work. It's a lot of sort of making sure you're very careful as you write the solution out. Go ahead.
So I was just a bit confused about the plot. Was it theta in the x direction and then mu s in the y direction?
It was radians. So it was radians on the x, it was mu sub s on the x-axis and radians on the y-axis. Go ahead.
Do we have to derive the rotational inertia of a rod at the end of it every time, or can we just write it as 1/3?
You don't have to derive those. Okay, I've written it out and derived it for you in this particular example because I don't think I've done it enough. But at the same time, if you take a look at your, has anyone looked at the crib sheet yet for the final? Yeah, take a look at the crib sheet for the final and look at what's in there. You are allowed to put whatever you want in that crib sheet. At this point, you have less room than you had in the midterm and the quiz. So at this stage, it's really important that you start pulling that out and look at it and see what material you want to keep and how you want to organize it. The last thing you want to do is show up at the final exam and never having looked at the crib sheet. Okay. Oh, God. I have to see if I have an easier problem. I don't know if I want to do. Oh. Maybe I'll do an easier one. You have this thing sort of swinging. And again, with typical sort of cases when things are swinging, they sort of move back and forth. As it sort of moves up, it's going to move up at an angle and sort of do stuff. The total kinetic energy of this thing, it's at that instant, and ignore sort of the small little gap between O and the top, V sub G equals omega, I'm going to call that AB times H. So as this thing swings, it's sort of got a velocity, and it's rotating about that point. T is equal to 1/2 m omega squared h squared plus 1/2 Ig omega squared, which equals 1/2 mh squared plus ig omega squared. Okay. Which is again the parallel axis theorem. And so as this thing is moving, and it has a velocity, and all I'm asked for in this particular problem is the kinetic energy, I end up with the same expression as I've had before, which is the parallel axis theorem, mh squared plus ig, or ig plus mh squared. And so the total kinetic energy of this object is just going to be 1/2 the rotational velocity of it about the point O. And again, you'll notice that I'm not dealing with a point on the rigid body. It's not on AB, it's at point O. But that's how the rotation is moving with respect to that. Any questions on this one? I'm afraid I'm going to have to do my pulleys. Pulley and cylinder. Nope. Pulley with odd shape. Okay. All right. I always regret starting this one. This is a good one. It's nice. Okay. You're going to have to think about this one a lot. Go ahead. Sure.
Could you explain the terms before when it was separated into translational and rotation about G?
This one? This one? Yes. Right.
Explain these terms if I were to just look at it like this without combining them.
What do you mean? That's kinetic energy. That's the first lecture we did in this section. So we re-derived these relationships. Right here. It's that same relationship, right? So the derivation of that, if you want to go through it, I did in lecture 27. So it's a full derivation, and there's a video already out. I hope, if I'm active enough to do it. There you go. That's the full derivation. You include the rotational term. You have a relative velocity for that individual. You integrate over the entire body. Half of it disappears because you do it about the center of mass. And as you continue through all of this stuff and calculate all of the individual kinetic energies, you end up with this relationship right here. VI dotted with VI. And all of the terms in the center go away. The VGX omega y, omega y, and VGY omega x. And the only terms left are translational and rotational. We don't rederive this, though. So when I get to this problem this week, what did I call this? No. Swinging beam. There we go. I'm going to immediately write it that way because I have general plane motion. I know that. And because I have general plane motion, I'm just going to write I have translational plus rotational. Now, I'm also going to look for a point, in this case, of 0 rotation, or instantaneous center of 0 velocity. And maybe now's a good time for me to sort of go back a little bit to my 2-bar linkage. And yesterday when I derived it, I sort of said, hey, we can do this a number of different ways. But over and over, when it comes down to it, and if I have a choice, I will never do anything with graphical approaches and instantaneous centers. I think you may remember the lectures where I desperately try to avoid instantaneous centers. This is the same thing, same result, and it just shows you get the same result out of that. This set of lectures should be out, I think tomorrow, or tonight, tomorrow, when I get a chance. All right, pulley and cylinder, no, pulley with odd shape. All right, back to this. So this is more involved, and it's not more involved because there's lots more to it. It's more involved because it's harder to sort of visualize certain things. And some of the things I'll point out right now is that this velocity here is going to be dependent on the 2 velocities on either side of it. So if you look at that, you know that the angular velocity of I and O, so inner and outer, are the same. But you also know that the linear velocity at the point of contact of the belt at point I and point O are different. And so the belt has a difference in velocity across it. So the other thing that you're given here is it's a double pulley, so it's not a uniform mass. And when you have double pulleys, you'll see examples of that, I'm sure, in the lecture or in various sources. You end up with a radius of gyration. So K sub D, again, is a radius of gyration, not a spring constant, and you can tell because of the units, and you should keep your units with things, just again, sort of waving that flag. 10 centimeters, RO is 15 centimeters, RI equals 7.5 centimeters. It's connected to the pulley at P, which has a radius which is R. And you can guess right now that the radius of that is going to be 1/2 15 minus 7.5. The radius of gyration of this is given as 3.5 centimeters. So we're going full tilt on that. Find the speed of the crate C, which is down here, and find omega D. Omega D, oh, D is the larger pulley. So the angular velocity of the larger pulley after the crate has dropped 2 meters. So lots of stuff happening here. All right, it's complex in so many different ways. But you're asked for a force because you have a weight, and you know that weight is going to cause things to move. Because if I remove my finger and let it all drop down, or remove my hand, it's 20 kilos, it's going to drop down. There's going to be an associated velocity. There's a force, and there's a distance, and that's that 2 meters. So I have force, velocity, distance that I'm solving for in this particular problem. But it's also going to be angular distance. All right. Yeah. I have the weight. I have Gx. I have Gy. I have 3 points of contact, and I'm going to refer to these as F, E, I, and H. And good for me, I did not include a G there. All right, so I have I and F have the same velocity, same linear velocity. E and H have the same linear velocity. But I and h have a difference between the two. I have the weight, which is acting downwards, of that pulley. So in terms of free body diagrams, this, again, it's not so bad. There's only the two weights, and the reaction force is at the pin. You've got tensions in the cable, but we're trying to sort of skip over them for now. Now, the upper pulley doesn't move. It doesn't go up, it doesn't go down. The lower pulley does, and the crate goes. So both of those are moving, and I haven't done the free body diagram for the crate. Now, I'm not doing a force balance, so I don't worry too much about what's happening in terms of sort of internal forces and things like that. I'm going to sort of ignore everything. I just want to look at everything sort of all together simultaneously. Again, really complex motion here. So I have T1, which equals 1/2 mc vc1 squared plus 1/2 ig omega d1 squared plus 1/2 mass of the pulley, velocity a1 squared plus 1/2 ia omega a1 squared. Okay. T2, on the other hand, is 1/2 mc vc2 squared. Not really on the other hand, same thing. ig omega d2 squared plus 1/2 mass of the pulley, velocity a2 squared plus 1/2 ia omega a2 squared. So all of the kinetic energies of all of the things happening at this time. Now, one of the things I know about this particular system, again, from sort of the setup, the pulley D doesn't translate. So there's no translational velocity. The crate moves, but it doesn't rotate. So the tricky bit is this bit here, recognizing that the pulley will have both a rotational kinetic energy and a translational kinetic energy because the pulley P is moving. It goes down. All right. And so the two potential energies are just going to be gravitational potential. There's no change in, there's no springs, there's no friction that we're sort of dealing with. Everything is there that I need. But my problem is this pulley over here. So if you recognize E and F, you know that velocity of E is equal to minus R naught omega dj, and velocity of E equals, h and I. Velocity of h. Because they're both attached to the same belt. So if they're attached to the same belt, they have to have the same velocities. However, velocity F has the same let's make everything vectors. So velocity E equals r naught, the outer radius of the large pulley, times omega d of the large pulley. And all I've done is I've calculated the vector product, and I just put the negative in there. I'm not doing r cross omega in this case. I'm just sort of putting the answer down there. At this point again, this is something I think that's useful if you don't want to calculate vector products in the course. Just put what the result looks like, A, B, C, and D, and you'll be fine. So you can say velocity of I equals velocity of h plus omega p cross with r I relative to h. So you can find, from that, you can find out what the angular velocity of the pulley is, because it's going to be twisted. One will be going faster than the other. And so putting in all the terms that you have, you have velocity of I, which you found from the upper pulley. You have velocity O, which you found from the upper pulley. You have also omega pulley, which you don't know, and the distance between I to J, or I, oh, which one am I solving for? H, I with respect to H is 2R. And remember, I'm using this notation. So omega of the pulley is equal to r naught minus ri all over 2r omega d. So looking at the geometry in this case, I can say, well, the difference between the two, the r that I need to know, is 1/2 the difference between the outer and inner radii. And since I want 2r, I can just multiply that by 2, and it's just the difference between the two radii. And so if it is, and I substitute this back in, omega of the pulley equals omega of the larger pulley. Omega of the small pulley equals omega of the large pulley. All right, so substituting in terms, putting everything in, I now have a relationship for one to the other and everything all together in between. So if I look at that as a last step, I just want to make sure I keep H and I correct. H and I the velocity of the crate is the velocity of the center of mass. So whatever velocity of the center of mass is as it drops, it's the same velocity as the velocity of the crate. So I can do the same thing I just did, but now instead of 2r, I'm going at distance r. Ugh. So it's going to be the same thing. It's just going to be half. Everything sort of works out. Velocity A equals velocity of the crate, which equals minus 1/2 r naught plus ri, omega dj, vc squared 2 equals va2 squared, which equals 1/4 r naught plus ri squared omega d2 squared. And oh, I got to do a lot here. I got 4 minutes. I can then write v1 equals t1 plus t2 and plus v2. So T2 plus V2. T1 is equal to 0 because this is starting from rest. It's released and the whole thing sort of goes. And you end up with a whole bunch of terms, which we've already derived. So I'm going to skip past the rewriting of those and just give you the final results so you can do them on your own. GH. And omega t2 vc2 equals twice gh mc plus mp r I plus r naught squared, square rooted, all over 4 kg squared md 4 ka squared mp plus mc plus mp ri plus r naught mess squared. All right, those are just to get you to here. You're not, again, you're unlikely to solve them this way. You are more likely to just put numbers in earlier. And you get a final velocity of the crate of 5.02 meters per second and an omega of 44.6 rads per second for the pulley. This is a complex geometry. There's a lot of things happening, but it's actually quite remarkable that you're able to solve all of it with relatively simple analysis. And when I say relatively simple analysis, this right here, the fact that you're able to just use the free body diagram, recognize, using the relative velocity equations, how to relate the velocity of the larger pulley to the smaller pulley, and then extract out